Alright, so in this video I want to talk about solubility. Turns out that the solubility of a compound depends on equilibrium, just like everything else we're doing. So look at this for example. We have calcium fluoride, and calcium fluoride dissolves to make calcium and two fluorides. Now the thing about this is it's in equilibrium, but notice that what we started with was a pure solid. So if we write the equilibrium expression for this, we're going to say the K value is going to be equal to the products over the reactants raised to the coefficients, but excluding solids. Well, if we don't include the solids, all we got are the products multiplied by one another. And then since we got the F, we'll square it like that. So in this case also, we label the K value KSP. That's for solubility product. So anytime you see a KSP, we're talking about dissolving something. So that's how that works. All you have to do to figure out if something's at equilibrium is look at how much of it is dissolved. So I already talked about that. Solids are out. The value of the solubility product constant, the KSP, is a measure of the solubility of a compound. I gave you the table that has KSPs in it. It is posted on my website as well as Google Classroom. It's the big one, not the small handout, but it's the big one that I didn't pass out because it's so long. So next thing we're going to talk about is something called molar solubility. And molar solubility is the solubility in moles per liter. So essentially, the molar solubility is going to be represented by an S, and that's why you're seeing like the S's here at different places on this page. But the S is equal to your X in an ICE table. So if we try to figure out the molar solubility of silver chloride, for example, okay, KSP isn't the molar solubility, but you use it to find the molar solubility. So we're looking at KSP being equal to your silver and your chloride, okay? Now, if you were to turn this into an ICE table, essentially what that means is KSP is equal to X squared, because both of those, since there's just a 1 in front of each of them, they would turn into X. So notice that the KSP for two products is S squared. So the molar solubility squared. What we mean by two products is you have two ions, okay? If, for instance, we had, think of something, anything that has two, two cations or two anions. So if I had like zinc chloride or something and it's ZnCl2, well, now we have a 2 here, and that makes three products. So your solubility, molar solubility would follow that, because what we would end up with is your KSP being equal to X times 2X squared. So that goes to X times 4X squared, and then that equals 4X cubed. So this is how we get 4S cubed. Anyway, if you want to solve for the molar solubility, you just solve for X. So in this case, we have the KSP value of your silver chloride, so we would do 1.77 times 10 to the negative 10th is equal to S squared. Take the square root, and you would get this as your answer, and that's the molar solubility. So in this case, what you're going to do, I'm not going to work the whole thing out, but PbCl2 has three things, because when it splits up, you're going to get Pb2 plus and 2 Cl minuses. So that means your KSP is going to be equal to 4S cubed, like that. So then solve for S, you should get your answer right here. All right, so here is the important thing. You cannot compare the solubility of compounds based on molar solubility, because molar solubility depends on the stoichiometry of the dissociation. So what we're saying is, one compound that has more things, like your lead 2 chloride, 1 mole of that is going to make 3 moles of ions, whereas 1 mole of the silver chloride is only going to make 2 moles of ions. And so it's not a fair comparison. So obviously there's more that's going to end up in solution with the lead compound than the silver compound. So you can't compare molar solubilities. The only way you can compare molar solubilities to figure out which one is more soluble is if they have the same dissociation stoichiometry. So if they each have 2 ions that are made, or they each have 3 ions that are made. Otherwise, you can't compare them. You'll just want to stick with the KSP values. Now, with solubility, you also have to take into account common ions. Remember Le Chatelier's principle with equilibrium. If you add a product to something at equilibrium, it's going to shift more toward the reactants. If you add a reactant, it's going to shift more toward the product. So in this case, there are no reactants when you're dissolving something, because you have the solid on one side and then you have the ions on the other side. And so really all we care about are the ions. So if you already have, let's say we have, we'll just do the silver chloride thing again, but I had already put in sodium chloride into the solution, well, that means chloride is already there, so it's going to hinder silver chloride's ability to dissociate, because there's already going to be some chloride in the solution. So what's the molar solubility of calcium fluoride in a 0.1 molar sodium fluoride solution? Well, how you would do this is you would say, okay, well, we have our calcium 2 plus and our fluoride, and obviously there's 2 of them, but we're going to start with 0.1 molar here, and then we have 0 of the calcium for our initial. So what that means is when we are working the problem, we're going to say, okay, well, we're going to add x here, and we're going to add 2x here because there's a 2 there. And then we're going to end up with x and 0.1 plus 2x. And remember, in this case, x is also S. So S is the molar solubility. X equals S. So what we're going to do now is we're going to solve for S, or x. So 1.46 times 10 to the negative 10th is equal to, and then remember all these are products, so I don't even need that line. We're just going to say, I'm going to convert them to S now, times 0.1 plus 2S, and then I got to square that one. In this case, 10 to the negative 10th is way smaller than the starting concentration, so we can do the x is small, or in this case, the s is small approximation. So what we end up with is s times 0.1 squared. And now you just divide by your 0.1 squared, and you end up with this as your answer. So that's really all there is to it. Now this is, over here, this is your ice table. Sorry, I probably should have done that, but there's no reactants in this one because this is a solid. Alright, that's all. I'm going to stop there for this video.